So, we will conclude this module and this course with some practice problems. Okay. Now, before I start the practice problems, I just want to mention that where we have done this Frobenius method, and it is a very general method, and there are a very large number of problems that can be solved using the Frobenius method. You can write down any number of differential equations and try to solve them using the Frobenius method. You can write down a differential equation by yourself, okay, make sure that it is that you can solve it using the Frobenius method and try to go ahead and solve it. So, in that sense, I won't be doing those kind of practice problems. Okay, what I'll just show you a couple of examples, okay, where of fairly straightforward practice problems that you can get, but for those who are interested in learning more and getting used to these, okay, you can make up all kinds of practice problems, or you can even look them up in various books. Okay, so let me do I'll do a couple of short practice problems. Okay, so the first one is has to do with the use of the Frobenius method. Okay, so I'll just state the problem. So for what value of alpha can the differential equation, okay, x square y double prime plus 2x minus alpha x square minus 1 y prime plus alpha by x plus 1 y equal to 0. So be solved by Frobenius method about x equal to 0. Okay. So basically I am asking that for what should be the condition on alpha, so that you can use the Frobenius method to solve about x equal to 0. Okay. Now you can clearly see that x equal to 0 is a singular point, because a of x equal to x square equal to 0 at x equal to 0. So clearly, since this term, okay, that is multiplying y double prime, okay, is x square, and that goes to 0 at x equal to 0. So x equal to 0 is a singular point. Okay. So then what should you do? You look at b of x divided by a of x and c of x divided by a of x. So b of x is basically 2x minus alpha x square minus 1, c of x is alpha by x plus 1, and a of x is x square. So we look at these two, and then we decide whether you can use the Frobenius method and what should be the condition on alpha in order to use the Frobenius method. So let me just write that you have a of x equal to x square, b of x is equal to 2x minus alpha x square minus 1, and c of x is equal to alpha by x plus 1. So suppose I look at b of x divided by a of x, okay, so that is equal to 2 by x minus alpha times alpha, okay, plus alpha divided by x square. Okay, so you have three terms. So I just opened the alpha times x square minus 1, and I got these three terms. Okay, so I divided by x square. Okay, so you get this. Okay, now I deliberately wrote this in this form. Okay, and you can immediately see the advantage of this. So as x tends to 0, b by x divided by a by x, okay, tends to alpha by x square if alpha is not equal to 0. Okay. So as x goes to 0, alpha by x square is much greater than 2 by x. Okay. So this goes as 1 by x, this goes as a constant, okay, whereas this is going to infinity. Okay. So, alpha by x square is the largest term as x goes to 0. So, if alpha is not equal to 0, then b by x by a by x goes as alpha by x square. Okay. So, this goes to 0 faster than 1 by x. Okay. So, this goes to 0 faster than 1 by x, and so you cannot use the Frobenius method. Okay. So, that immediately says that cannot use Frobenius method. Okay. So, when can you use the Frobenius method? So, if alpha equal to 0, okay, then b by x, b of x divided by a of x goes as 2 by x. Okay. So, this does not go to 0. So, this does not go to 0, does not go to 0, goes to infinity, does not go to infinity faster than 1 by x. Okay. So, if alpha equal to 0, it appears that at least the b by x by a by x is fine. Okay. What about the c by x by a by x? So, c of x is alpha by x plus 1. Okay. Now, if alpha equal to 0, okay, then it is just 1. So, if alpha equal to 0, c of x equal to 1. Okay. And what do you get? C of x divided by a of x equal to 1 by x square, and this does not go to 0 faster than 1 by x square. So, it goes to 0 as fast as 1 by x square, but not faster. Similarly, this go to infinity. I am sorry, I am making this mistake repeatedly, but it should be go to infinity. Okay. So, c by x by a by x does not diverge faster than 1 by x square. Similarly, b by x by a by x does not diverge faster than 1 by x. So, okay, so the solution, so the condition on alpha is alpha equal to 0. So, if you want to use the Frobenius method, then alpha has to be equal to 0. So, if alpha equal to 0, Frobenius method can be used. Okay. Okay. So, this was the first problem. Now, the second problem, and here we will focus on setting up the problem. Okay. So, show that quantum mechanical confined particle, okay, in a circle, okay, satisfies Bessel equation. So, particle in a circle. So, the particle in a circle, okay, the typical quantum mechanical particle in a circle satisfies Bessel equation, and you know I have not stated the entire question, okay, but you should say that v equal to 0 inside circle, v equal to infinity on and outside circle. Okay, so that is the condition. Just like the particle in a box, okay, you can have particle in a circle, and what I am asking you is to show that this satisfies Bessel equation, something that looks like a Bessel equation. So, your Schrodinger equation okay, now you have minus h bar square by 2 m. Now you have a Laplacian in you have a Laplacian. I will just write it as del square psi, and psi is a function of x y. So, I will write this plus v of x y psi of x y, is equal to E times psi of xy. So, this is the Schrodinger equation. Okay. Now, what we will do is we will write this in, so write it in polar coordinates in it and use V of r theta equal to 0 if r is less than some radius, I will call the radius as capital R, and equal to infinity otherwise. So, if r is greater than that radius, then it goes to infinity. Okay. So, what we do is just like in the particle in a box, okay, what you need to do is to write this Laplacian in polar coordinates, okay, and you need to set v equal to 0 inside the box. Okay. So, what you will get is minus h cross square by 2 m. Okay. Now, you will get the Laplacian in polar coordinates, we have already seen that. Okay. So, we have d square or dou square by dou r square of psi. Now, psi is a function of r theta, okay, plus 1 by r dou by dou r of psi of r theta plus 1 by r square dou square by dou theta square psi of r theta is equal to E times psi of r theta. Okay, so, this is the Schrodinger equation that you have, okay. And now suppose you do a separation of variables. So, separation of variables. So, what you will say is psi of r theta is equal to, I will say r of r times, I will just say y of theta. Okay. Now, when I substitute in this, what I will get is minus h cross square by 2 m. Now, I will get d square by d r square of r, and you will have the y outside, plus y by r d by dr of r, and then you have plus y by, or rather in this case you will get r by r square d square by d theta square of y. Y is only a function of theta, and this should be equal to E times r times y. Okay. And if you divide by this, if you let's say you multiply by r square, okay. So, suppose I multiply by r square and divide by r y, divide by capital R times capital Y, okay, then what I will get is the following. And let me take this 2 m e by h cross square on the right. Okay. So, what I will get is minus 2 m e by h bar square, and I will multiply by r square. Okay. So, I will just multiply by r square. So, I will have this, okay, and I have divided by r y. So, I will not have the r y term. Okay. And what I will get here is d square r by dr square times 1 by r, okay, plus r times dr by dr and divided by r, plus d square y by d theta square times 1 by y. Okay. So, what you have, okay, so you get an equation of this form. So, we just rewrote the Schrodinger equation after separating variables. Now, what is the advantage of this is that these two terms depend only on r, this depends only on theta, and the right hand side depends only on r. Okay. So, that means this theta dependence has to be a constant, okay, because if it is a function of theta, then the right hand side there is no function of theta, okay, left hand side cannot be a function of theta. So, this has to be a constant. Okay. So, that means you immediately get d square y by d theta square into 1 by y equal to constant. And we have seen this earlier, okay, we have seen this earlier when we are dealing with spherical harmonics, okay, since theta goes from 0 to 2 pi, okay, we can write this in the following form: y is equal to e to the I m theta, okay, and there is a factor of 1 by root 2 pi, but I won't bother that, okay. So if I want, I can write 1 by root 2 pi e to the I m theta, where m is equal to 0, plus minus 1, plus minus 2, and so on. So we have this, and then you can immediately see that d square y by d theta square, okay, is just minus m square y, okay, it is just minus m square y, okay. So now you can take this and you can substitute in this equation, and you can replace this whole quantity by just minus m square, okay. So what you are going to do is to replace this by minus m square, okay, and for convenience let me just call this alpha square, okay, I will just call it alpha square, it is a positive number, okay. So then what I will get is I can write my equation in the following form. So this equation I can write as 1 by r d square by dr square of r, plus what I have is r by r, okay, dr by dr. So that will be as it is. So r by r dr by dr, okay, and then what you have is this quantity is just minus m square. So then I just write this as m square. So this is just minus m square. So what you have here is just minus m square, okay, and this, and I'll bring the alpha to this side. So I'll just write this as alpha square r square r square, okay. So plus alpha square r square equal to 0. So suppose I just multiply by capital R, okay, then what I'll get is d square r by dr square, okay, plus r dr by dr, okay, plus r square, okay, alpha square minus m square times r equal to 0, okay. I just check once again, make sure I got all the factors, okay. So when I multiply by r square, there should be an r square here, sorry, there should be an r square here, there should have been an r square here, okay, that is good. So you have an r square here, okay, and you have this r square here, okay. So just to say it again, so when I wrote I multiplied out by r square, I should have an r square here, okay. So I had forgotten to write that, but now we can see that once we put that, okay, then you get this exactly like the, so if you want, you can just make a change of variables from you can just put s equal to r alpha, okay, if you want, okay, you do not have to do it, okay. So but if you do that, okay, then you can immediately see that you will get a Bessel equation. V equal to m, okay. You can get a Bessel like equation, and when we would have expected this, because because the problem that we have, the quantum mechanical particle confined to a circle is just like a circular drum, okay. So you have a Schrodinger wave equation, okay, with the drum boundary conditions, okay, and incidentally, okay, you can verify that if r is, okay, actually let me change the label for the radius, I will just call it a, okay, a is the label for the radius. You can verify that that the boundary condition it will basically be related to J m of alpha a equal to 0, okay. So basically alpha will be related to the roots of the Bessel function, okay. So that means alpha a should be is a 0 of the Bessel function, So this is how you get you solve the problems with circular boundary conditions, okay, and indeed it is because the zeros appear at distinct levels at distinct points that you actually get the quantization of this circular of this particle on a circle. Okay, so with this I'll stop here. Okay, so I'll stop, and I hope I've been able to show you some of the nice applications of the Frobenius method in chemical problems through this. Okay, and I hope that through this course, okay, we have been going quite fast. We have been doing lot of topics. Okay, but hopefully if you have taken this entire course, and you will feel confident enough to practice all these problems or to practice more problems on your own, and to go ahead and try to actually solve various problems in, especially in quantum chemistry, okay, with this knowledge of mathematics. Thank you.